Hi everyone. Here we have our first lecture today with our video series for this chapter. This chapter is called Electricity. So now we're going to get into the actual details about what happens when we plug things into the outlets, what all those things mean. So we're going to start with some basics. These things we kind of talked about a little bit before. All basic batteries have three components. The positive side, which is generally always the little knob, that's called the cathode. The anode is the negative side, generally the bottom. And then there's the electrolyte. So in this picture here, they actually took a battery, they cut it in half with a saw. By the way, you should not do this at home. It's very dangerous actually. But you see, here is the entire rod. This entire part is the cathode, but this is only the part that we see. The bottom here, if you look here, it looks like there's a casing all the way around except for at the bottom. That's the anode. And this black stuff right over here, that's called the electrolyte. Now there's some special things about the electrolytes. The actual electrolytes steal electrons from the cathode and bring them to the anode. That's what the whole chemical does. And the electrolyte is actually acidic. And this is why you shouldn't do this at home. If you guys try to do this at home and you cut open a battery, you'll get severely burned. You don't want to do that. These household items are a little bit safer than car batteries because these household items are called dry cell batteries. And what that means for us is that the electrolyte in there is very thick paste, almost like a peanut butter consistency. So if something were to happen at your house, and the battery would start to leak, it would take a long time for the actual acid to leak out of there. Because the last thing you want to do is have a battery in your remote control in your hand and acid start dripping out your remote control. That's not good. So the whole idea of having it a thick gel is that it takes a long time to really rust out of there. Whereas here, we have a picture of a car battery. And these car batteries, they actually have liquid, like sloshing acid in there. If you guys were ever in a car accident and your car flips over, you'll oftentimes see the actual battery acid start to come out the top of it, and it will actually dissolve some of the metal. You need to recycle all batteries, particularly these wet cells, because the last thing you want to do is throw a wet cell battery in the garbage can, the garbage truck takes it up, and when they go to compact the back, it pops like a balloon and someone can get really hurt. So you really need to save these guys. So when connected to a wire, electrons want to leave from the anode and travel to the cathode. Think about electrostatics, how negatives want to go towards the positives. This is called DC or direct current electricity. Battery operated things is direct current. So whenever you guys hear about AC/DC, whenever they mention DC, direct current, that's anything that uses a battery. Current, by definition, is the charge moving in a given time period. So this right here is the first equation. You guys do not have to memorize. I will give it for you. Notice it's located in a box. In this case, I stands for the current, and the unit for that is A, or amps. Q, as you guys know from last chapter, stands for the charge. And T stands for the time. So obviously the more electrons that move in a wire, the more current you have. You could think about current as kids in a hallway. If there's a lot of kids in the hallway, there's a lot of traffic. So you could think of traffic as current. So there are some ways that we could increase the current in the wire / make more people move in the hallway. So we can use a thicker wire. You guys may know from experience, if there's a very thin hallway, you generally tend to go very slow because the people in front of you guys are going slower. But if you're in a bigger hallway, a thicker hallway, that means you guys can go around the slower people or the people that are doing crazy things in the hallway. You could also use a shorter wire. The philosophy here is that the longer the wire is, the more something can go wrong that will slow you down. So using very short wires will increase the current. You could also use better conductors. So you can think of the hallway as we do here. Sometimes it's carpeted, and that's perfectly fine. Sometimes there's tile, and that's perfectly fine. But imagine, if you would, sometimes there's a rut in the carpet, or an area where there's a leak and the garbage can is in the way. So the more clear the hallway is, the more traffic we can actually have in the hallways. And lastly, we can make the battery stronger and decrease the overall resistance. And what exactly do we mean by resistance? Resistance describes the electrical strength of components. So if you guys have ever seen any kind of science show at all, and they have the computer chips, these little blue and tan guys are probably welded directly to the motherboard. Okay? If you guys remember WALL-E, Eva had to find all the different motherboards. These things here are basically attached to the circuit so that your computer doesn't get too much electricity. All these different colors stand for different values. So these blue ones, I can tell you for a fact, they're a lot stronger than these tan ones over here. And all the colors give you the exact value of things. So why exactly will we use these as current managers? Let's say you have a battery and you have a hearing aid. And obviously the battery will last a long time. So you want to make sure that the hearing aid doesn't use all that electricity at once. So you add a resistor into it to make sure that the battery is not overwhelming the hearing aid with current. But besides resistors, actual resistors, things like light bulbs have resistances to them too. Basically anything that you can plug into something and it works, quote unquote works, can be a resistor. So for example, your cell phone going off. What happens when your cell phone goes off? It lights up, your screen lights up, right? It makes sound. So there is something else that has a resistor to it. Your phones move, they're on vibrate, so they move. Those are all things that require electrical strength. Those are all things that have resistances. The unit for resistance is ohms, or if you guys have ever been on 130, you'll recognize this symbol as the omega dyna. This is actually a Greek letter, it's the last Greek letter. You could either do the horseshoe, what we call omega, but for a science class we're going to say it's ohms, because that's what that symbol represents. Here is the equation for the resistance in just a wire by itself. This is not for an actual component, this is just the wire. Okay? So R equals PL over A. So A is the cross-section area, aka the thickness. So obviously, once again, according to this equation, the thicker the wire, the smaller the resistance will be. Once again, the same idea before. The bigger it is, the more people can actually fly through it. In this case here, the longer it is, the more resistance you have, because L is going to be the length of the wire. And this guy P, the resistivity, is basically unique to the metal. So most of the time we're going to use copper, so that P will always be the same thing for us. And R, once again, is the resistance. You guys may have noted in those cable lines, those large cable lines outside, if you would, every so often there's a electrical tower. And those towers are there for stability, but over long distances, that's when this equation actually has something to do with it. It's not going to affect your house, so you don't have to worry about that. This is talking about transcontinental power lines here. So here's a sample question that incorporates both pieces of this. A 1,000 meter copper wire has a thickness of 0.05 meters squared. The resistivity of copper is 1.68 times 10 to the negative 8 ohms per meter, or ohms meter. 40 million electrons can move in this wire in 10 seconds. So what is the resistance and what is the current? So let's look at this. In this case, we got a T is 10 seconds, because we don't forget the givens. The resistivity of copper is 1.68 times 10 to the negative 8, like so. Ohms per meter. The area of the wire the cross-section area, if we cut it in half, and you guys look down the bottom of it, you would see that. And the length of it is 1,000 meters like so. So let's address the R first. So we're going to use the equation for resistivity. And in this case, we're going to get 1.68 times 10 to the negative 8, 1,000, all over 0.05. Just like that. Remember, folks, when it comes to doing scientific notation, since this piece right here is the only exponent we have, we can just carry it down and then do the rest of the math. So we can do R equals 1.68 times 1,000 divided by 0.05 and get 33600. And once again, since that's the exponent, times 10 to the negative 8 ohms, like so. But notice this number is actually not in proper scientific notation. So we have 1, 2, 3, 4 more spots. Notice I'm moving the decimal point 4 spots to the left. So this number here has to get bigger. So we have here 3.36 times 10 to the negative 4 ohms. And that's the natural resistance in this cable. 1,000 meters isn't that bad, but it's a very small, thin wire. You would never see this much wire in an actual power line outside. This thickness of wire would be more something like in your cell phones. This leads us to the next question. In this case, they're asking for I. What is the current? So we're going to use I equals Q over T. Now, the T they give us, the Q, they don't specifically give us, but they do tell us that there's 40 million electrons. You guys know from experience the charge of one electron. And if you guys don't remember that, the charge of an electron is negative 1 point, you guys remember it? 6 times 10 to the negative 19 coulombs. So how exactly can we figure out what the actual charge is that we put into here? Well, if this is the charge for one electron, then if we have 40 million electrons, we can set up a ratio. And if you do that, you basically times this guy by 40. So the Q is going to be, I'm sorry, not 40, 40 million. So 40 million times 1.6, you get 64. 1, 2, 3, 1, 2, 3, times 10 to the negative 19 coulombs. And once again, this is not proper scientific notation, so 1, 2, 3, 4, 5, 6, 7. This number here is going to increase by 7. So 6.4 times 10 to the negative, in this case it's increasing, so negative 12 coulombs. That's the charge that's going to go into the calculation. So in this case here, I will equal 6.4 times 10 to the negative 12 all over 10. Now for us, if you guys remember anything about scientific notation, that should be 12. If you guys remember anything about scientific notation, dividing by 10 basically means that this number is going to get a little bit smaller. So all we have to do is just move the scientific notation over. And in this case, we're going to get 6.4 times 10 to the negative 13 amps. And that's how you find the current naturally just looking at the electron.